just in case I forget to say it in the middle, so we're going to be using a new set of tools, of optimization tools for the materials we're covering today that you'll use on your problem set. And there's instructions in the problem set to help you with this deal. But there's a one extra solver that you'll need to install to use along with the MATLAB solvers. MATLAB's going to call a solver that can handle the types of problems we generate, the convex optimization problems we generate based on the material today. So you get your pick. You can install, if you love open source, then you can install Sadoomi, and it's free to the world and everything, but it's a little slow. And if you want to, if you don't mind installing the commercial solver and using the free academic license, it'll be faster and numerically a little better. So you have a moral decision to make. I installed Mosaic personally, which is the commercial one. Okay, so last time I tried to give you the background we needed to talk today about one of the topics that I'm actually most excited about, that we pursue very actively in the research group right now, which is using optimization to do the Lyapunov analysis that we talked about last time. And I hope to convince you, partly today, but over the next few lectures too, that it's about more than producing proofs that a system is stable, but it'll actually help you in the control design process. So today is about Lyapunov analysis using sums of squares optimization. And so it's a bit of a tall order here to tell you all the pieces that we need to make you understand this story completely. So I'm going to do my best to give you the background only to the extent necessary to give you to understand the big idea here today. So we need to know a little bit more about optimization first. So we've seen optimization a few times in the class. It'll be a constant theme. A few examples that we've seen already, just to make sure it's all tying together. When we talked about the dynamic programming discrete update, we wrote down equations that said, for every s, I'd like to make some update, which is minimizing over a, right? GSA. The equation's not some. This is just to jog your memory here of SA, where this was the state transitions. This was my cost to go, right? But in the middle, we started using the language of optimization, right? We used this minimization in the middle, and in the discrete case, that meant literally you could write an algorithm that tries every a and take the minimum value. Right, so that was sort of easy to program. Right, I try every possible a, because this was only looking over a's in some discrete set of transitions in my graph, and I plug it into this equation, I get a value out. Whichever one is the smallest value I'm going to keep, and that's the output of my minimization. That's sort of trivial, discrete optimization. We've seen a couple examples in a continuous domain where we used the same language, right? We said min over u, and in the special case where we had some quadratic cost plus some f2u, if we had something that was quadratic only in u plus some other stuff, then in that case we said, okay, we can solve this minimization problem in closed form, because this thing, since I knew r was positive, then I know this thing is just going to look like some sort of quadratic bowl wherever it is. So if I look at different values of u, I know that it's going to be some simple thing like this. So I could actually find the minimum by looking at the place where the gradient with respect to u was 0 and finding that point. That was another instance another extreme where this was a continuous optimization. But we were able to solve it in closed form by just making a gradient argument, right? Now today we're gonna broach sort of the more complex forms of this optimization. So This already gets more complicated if I were to put some sort of constraints on u. Let's say if I added some bounds on u or other things, then this simple analytical solution doesn't work anymore, right? In general, right? So the general sort of nonlinear optimization is hard. It's a hard problem. So, right, if I were to, in general, use the language, I'm going to minimize over some decision variables alpha, some objective. Let me write that as just some big function of alpha. Right? In general, if I don't have knowledge of what f is, that could be a really hard problem. If I plot alpha, I could have some complicated function f of alpha, and there might be not much I can do, certainly in closed form or even with a computer, to find sort of the global minima of this without sort of brute force searching. It might be very, very hard. So if I write this down in general, it could be hard. I mean, our goal would be to find some alpha star, but it might be that we find some local solution, which I didn't give myself a very obvious local minima here, but it might be that I get stuck with something here if I'm just trying to look at gradients or something like this. I might get a very bad solution. It's hard to solve this problem in general. Okay, and the full-blown nonlinear optimization also allows you to encode extra constraints on alpha. I could say subject to some list of inequality constraints, G, that can be a vector G, right? Just so you have the language, this is a scalar objective function, right? This is my objective. These are my constraints. And these are my decision variables, right? Okay, so in general, optimization is hard. All right, so today we're going to talk about something that's maybe halfway between this general nonlinear optimization and the closed form solution. It's a problem that's hard enough that I have to ask the computer to solve it for me and just settle for a numerical solution instead of an analytical solution. But it's actually much easier than the full-blown nonlinear optimization problem, in the sense that there's a class of problems where if I ask the computer, I'm confident that it can efficiently find the global solution, right? So you can imagine that if f took a particular form, if f was some sort of easier function, in fact it's going to be a convex function, then I'm going to be able to rely on my computer to find the best solution efficiently. And similarly, if these constraints form a convex set, then I'm going to be in the world of convex optimization instead of nonlinear optimization. And it'll be surprising, it's been surprising to me how many problems can be formulated as convex optimization problems. And they have very efficient solvers available, which you'll download, either free or commercial. And they're going to be able to solve these problems for us almost to the extent where we could think of it as it being a closed form solution. Okay? So how many people know convex optimization? Feel like they've seen that before? Okay, that's about what I expected. That's good. All right, so let's just tell you a little bit specifically what I mean by convex optimization. So now this is a rich topic. You could take a whole semester course on it. I feel like I say this every lecture. It's really annoying. So it's a rich topic. You can take a whole course on it. I'm going to spend 5 minutes on it here, but I think you're going to have enough to be able to be extremely effective with the tools. Okay? Oh, I'm sorry. Yeah.
So when you're performing this, how do you know your value functions on the right hand side? So you have to know something about the convexity of that a priori to actually use this method.
So I wanted to put that in context with the value function stuff we did before. you're going to see immediate application today with the Lyapunov instead of the value function, and it'll be crystal clear in a few minutes. Yeah. So how would you use that in the value iteration loop? We have an answer for that too, but it's a slightly harder story. Okay. So what does it mean to be a convex function? I think you know intuitively what it means, right? So a function is convex in its parameters. If it's shaped up, if it's sort of pointing upwards like that, right? So what's the technical definition, right? So if I take any 2 points, let's call it alpha 1 and alpha 2, and I look at the function evaluated at those 2 points, then I should be able to draw a straight line between them that is everywhere above or equal to the function. That's how we're going to define a convex function. Okay. I can write that mathematically very simply. This line segment here is defined as a affine combination of those 2 points. So I could, if I make a number beta that goes from 0 to 1, and when beta is 0, I'm over here, and beta is 1, I'm over here, I could write that as beta alpha 1 plus 1 minus beta, let's say alpha 2. That would walk the line between here and here, right? That would parameterize this line segment down here, right? And what I care about, I should use my colors. What I care about is what's the function over that interval. Okay, so I would like that some linear combination of these points, which is going to be, let's say, beta f of alpha 1 plus 1 minus beta of f of alpha 2. Right? That's my combination of this. That had better be greater than or equal to the function evaluated at the point in between. So okay, that's just saying exactly what I said in pictures, that this line, the combination, and this is always for that, yeah, this line is everywhere above the function. Very simple definition, simple test. So our objectives in convex optimization should be a convex function. The other thing we need to understand is our constraints have to be a convex set. Okay, so intuitively what a convex set is if I have some region of possible parameters, let's say it's in alpha 1 and alpha 2, right? And I say any of these are okay. Then what that should mean, the definition of a convex set is if I pick any 2 points inside that set, then the line connecting them should also be inside that set. The line segment connecting them. Yeah. So exactly analogous, right? So if alpha 1 and alpha 2 are in some set, call it G, I guess, then beta times alpha 1 is 1 minus beta. 2 had better be in G. Okay, so my objective, you can imagine that if my objective is like this, it should be easy to find the minima. What the function being convex implies basically that there are no spurious local minima. There's no place to get stuck if I'm doing optimization. Yeah, and the set being convex is important for that too, because you could imagine. Let's give an example of a not a convex set, right? If I had some set like this, right, and this not convex, right? then you can imagine getting a solver getting stuck. If I've got some, even if I've got a smooth objective function and I'm trying to get down, then maybe I have to, maybe the minimum is over here, but I'm stuck here thinking I can't go any farther, if that makes sense. If I were to be looking at the objective along this line, it might look, even if the objective is smooth, there might be a gap in what I'm allowed that prevents me from ever looking and finding my path down to the real minima. So you need both in order to have an easy optimization problem. Does that make sense?